Okay, in this problem, I want to find the shear and bending moment diagram of the following loading on this beam. So the first thing I need to do, again, is find those reactions. So I draw a free-body diagram of the entire system. I need to find AY and BY. I've got the 900 force, and then the distributed load, which is 400 times 6, acting at the midpoint, which is 3 feet away from A. So if I sum the moments, set them equal to 0, I get, if I'm doing this about A, I get 9 times B, and then I get 6 times the 900 and 3 times the 4 times 600. Solve for BY, I get 1,400 pounds. Okay, summing the forces in the x direction, basically I get that 1,400 pounds, and then I have the 900 and the 2,400 here, giving me a y of 1,900 pounds. So again, just use statics to find the reaction forces. Now I need to make 2 cuts. I need to make 1 cut in the distributed load and then 1 cut on the other side of the concentrated load. So if I make that first cut, again, I'm going to cut at some arbitrary distance x away. I've got my reaction force 1900. I've got my distributed load, which is 400 times x, at a location half of that x over 2. Again, that changes as x increases between 0 and 6 feet. And then I've got my positive shear acting down, my positive moment acting in the counterclockwise direction. So summing the forces in the y direction, I get the 1900 up, I get the negative 400x down, and I get the negative v down as well. Solving that for v, I get an equation. This is my plot, what I'm going to plot, 1900 minus 400x. Okay. Do the same thing with moments. Sum the moments about where you cut it, that way v goes away. Okay, so you get your bending moment, positive bending moment, then you get a positive 400x times x over 2, that's what you have here, and then a negative x times 1900, and you get 19x minus 200x squared when you solve for m. Now what you can realize is I take a derivative of this, I get 1900 minus 400x, which is v. So that's that check that we had talked about between v and m. Okay, now I'm going to cut it over here between the 900 pounds and point B. I'll actually draw the right side of the beam, okay, make it a little easier, but recognize that's 9 minus x, because again, x goes from A over, so now I'm going to go from 9 back, so it's 9 minus x is the distance of this. So I have my 1,400 pounds. Now my positive V is acting up, and my positive moment is clockwise, okay? So opposite of what we did here, because again I'm coming from the other side. But again, I just sum the forces in the y direction. I get the 1,400 up, the v up. So that means v is actually a negative 1,400 pounds. Do the same thing with the moment. Again, you do it about where you cut. Okay, so at v, that way it won't show up. So you get your negative m here, and then you get 9 minus x times 1,400 right there. Solve this for m, and you get the 1,409 minus x. Okay. Now, I can take, again, the derivative of this. I get this constant that goes away, minus 1,400x. Derivative of that is minus 1,400, which is what I get for v. So again, the derivative dm dx equals v, which is a good check. So now I've got these equations. I can draw my shear and moment diagram. So my shear diagram from 0 to 6 follows this equation right here, the 1900 minus 400x. So it starts at 1900 and drops down, and then at x equals 6, I get negative 500. So it's a linear curve like that. Okay, and then moving on from there, it's just 1,400. So here's where that jump happens, right? So here's what you can do. At A, I jump up 1900, just like I have there. I follow my curve down like this. Then it goes from 500 down to 1,400 because I have the concentrated load of 900. Then it gets to B, and it bounces back up 1,400 because at B, I have 1,400. So that's where we talk about those jumps like we had before. Now, my moment diagram, again, this plot works from 0 to 6, and this goes from 6 to 9. So plugging in this moment equation, you follow a curve like this, noticing that it peaks right there at 4.75, at 4512.5, that'd be foot-pounds. But again, notice it starts at 0, because when x equals 0, this equals 0, right? When x equals 6, it equals 1400. Then it follows a linear path from this equation back down to when x equals 9, my moment equals 0. So it's a straight line from 4200 down to 9. So that's how you put together shear and bending moment diagrams.